Welcome everyone. Today I would like to talk about project 2108, efficient Fock matrix construction in localized Hartree Fock method. This work was done by Ioannis Savvidis and me, Eduard Zsurka. Our supervisor is Dr. Jan Simonek. Firstly, let's talk about the Hartree Fock method. It basically gives a solution to the Schrödinger equation of a quantum many-body system, which can be a molecule or a crystal. This algorithm gives us an approximation of the ground state, wave function, and energy of that molecule. On the right side of the screen, we can see a rough sketch of the most important steps of the Hartree Fock method. The implementation of the Hartree Fock method that we used was one made by Joseph Noga and Jan Simonek, which is an alternative diagonalization-free solution of the Hartree Fock equations. So if we turn back to the schematic on the right, we can see that this Fock matrix diagonalization step is quite an essential step in the algorithm. Basically, this implementation replaces this diagonalization with a matrix multiplication. And one might ask, why is this necessary? Where for linearly scaling methods and parallelization, this step is unwanted. Basically, it slows down the code, the whole algorithm. This implementation was done in Fortran, and our tasks were the following. So we had to replace this dense matrix times dense matrix multiplication that I previously mentioned with a sparse matrix times dense matrix multiplication. For this, we had to find a working implementation of this sparse BLAST library in Fortran, use the functions from this library to create a working new code, and test it. The testing was done with multiple molecules. We used 5 different alkenes with varying number of carbon atoms, and we can see these molecules in the top right corner. We also looked at a molecule called methotrexate, and we can see this in the center of the screen. The testing was done using a supercomputer located in Žilina, and out of the 18 compute nodes of the supercomputer, we had access to 4. Each node had 32 cores, which were organized in 4 CPUs. The first type of testing that we did was using this molecule methotrexate, and we choose to do testing on a single node, and we used different number of cores for the testing. We used 1, 2, 4, 8, 16, and 32 of the 32 available cores in the node. And what we observed is that the original code was in every instance faster than our new code. So this result was not very encouraging, but we thought that the advantages of the sparse matrix multiplication will shine through for larger systems. And that's precisely what we did. We looked at C30H62 and C36H74. These systems were larger than the methotrexate molecule. And we looked at the same number of cores for a single node, and we calculated this ratio, this eta quantity, which gives us a percentage value of how much faster or slower the new code is compared to the original one. And what we can see is that for some cases, this code indeed is faster. And we can see that for the larger molecule, it's almost all the time faster, except for the 32 node case, the 32 core case. After that, what we did is we took all of the runs for each molecule, and we averaged out this percentage improvement, and we ignored this 32 case because it's almost always the slowest case. And we can see the results on the right of the screen, and again we see that for the largest system we have a significant improvement of around minus 4.2% on average. It's not a huge improvement, but we can see that for other larger large molecules, there is certainly a slight improvement in the runtime, whereas for the small molecules, this improvement is non-existent, so it's actually slower. The last thing that we studied was how the number of cores affects the runtime. As maybe as previously also noticed, these kinds of runs don't necessarily go monotonically down in time with the increase in number of cores. What we almost always see is that for 8 cores, the code is the fastest, and we can understand this when we think about the fact that the 32 nodes inside the node, the 32 cores inside the node are arranged in 4 CPUs, and for both the old code and the new code we do see this kind of tendency for the 8 core calculation to be the fastest. So in summary, we have proven that the performance of the Hartree Fock algorithm can be improved by using a sparse matrix multiplication. We found that for the largest system that we tested, there was an improvement of 4.2% on average. And we also studied how other parameters of the supercomputer can be used to decrease the runtime of our code. This is all I wanted to talk about. Thank you for your attention.